colleague over here tries to get the microphone working, I'm going to start because I'm a high school teacher and I'm loud, so it's great. So good afternoon and welcome to School Without Walls. My name is Ashley Shrekdas and I'm the head of the math department at Wheaton High School. I'd like to thank our sponsors at the Washington Statistical Society Statistical Education Committee. Thank you. All right. And the Maryland, D.C., Virginia section of the Mathematical Association for America for helping us put on this event today. We would like to encourage you to join the WSS membership and the ASA. Membership forms are on the table near the entrance to the room. If you're joining both, please only fill out both sides of the ASA membership form. In addition, the WSS Student Travel Award applications are on the back table. We'll have an informal reception at Bertucci's after the talk where everyone will pay for their own food and drink. However, the manager has said it's okay if a few people order nothing. There are 4 different receptions there this afternoon. We're the smallest and they've set up a table for us in the main dining room. It's listed under the name Carol Bloomberg. All right, so let's get on to our presenter today. So Danny Kaplan is a DeWitt Wallace Professor of Applied Mathematics, Statistics, and Computer Science at Macalester College in St. Paul, Minnesota. He has authored textbooks in computational science, statistical modeling, and data science, and even nonlinear dynamics. In 2017, he was given the Cause Award for Lifetime Achievement for his contributions to statistical education. He is the leader. He's on the leadership team for the StatPrep.org, an initiative of the MAA, the ASA, and the AMATYC, funded by the
the American Math Association of Two-Year Colleges.
There you go, what he said. Carol Howard is the Associate Professor and Co-Chair of Mathematics at Howard Community College and a hub leader for the StatPrep project. She is currently engaged in creating pathways for success for students to and through college introductory statistics. She is enjoying the fun involved with putting data in the center of these considerations. It's my pleasure to introduce Danny Kaplan and Carol Howard for their presentation today on bringing science, statistics, and education up to date.
All right, so as a community college teacher, my goal really is to get our students to be critical consumers of data. We're not preparing them to be statisticians, but to really be able to engage. And it's become really more and more important as there's more available data and an emphasis on database decision making in the fields my students are going into. So I have a lot of health science students, criminal justice students, construction management, cybersecurity. So you can see where the role of data would really impact how they think about their field. So we really need to have them engaged in rich, contextualized data. And that really is a transition for us, both for our students and for our instructors. ASA's GAZE document really helps us think about what that might mean, right? They really talk about what statistical thinking means as opposed to mathematical thinking. Many of the colleagues that I work with have a mathematical background as teachers as opposed to, there's not a huge pipeline into statistical education right now. So making that transition has become more and more important. Really helping people conceptualize what some of the traditional tools like a confidence interval means. How is it different teaching a student how to calculate one as opposed to use and interpret one in a really rich manner. Really that power of technology has really opened the doors to what we can help them achieve. And really for our students, there's really an experiential difference between teaching them how to take a small data set, put it in their graphing calculator, right, and create a confidence interval, right, as opposed to grapple with a large data set and make some meaning out of that. And I think our students are beginning to realize that difference as well. So just today, I teach 3 sections of instruction statistics. We're reviewing for a test, and we're looking at confidence intervals and hypothesis tests. And we were doing a hypothesis test, and one of my students said, so my P is 0.048.
Ooh.
And my level of significance is 0.05. On the test, what happens if I round? And I said, well, what do you mean? Well, if it's 0.052 or 0.048, you're telling me you really care? And I said, well, maybe there should be some other tool we should be using to help describe describe our results. And it was lovely. She said, we should look at our confidence interval. And I thought that was such a powerful answer because she was struggling with this idea of, really, there's this strict cutoff that makes a difference between 048 and 052. So I thought it was good that she was also questioning, what does that p-value mean? And is there some other way to put that p-value in a context to help decide how important that hard cutoff is? So I thought it was a fun context for an exam review, and I really appreciate your input. In addition, both our students and faculty have to think more about how we can make it more accessible. So we want students to grapple with this data. Our solution before has been to use a graphing calculator, which I'm not sure what the limit of data is, but it's not strong and the graphics aren't great. As a community college, I've been having students come in with food insecurities, so asking them to invest in expensive programs is difficult as well. So when we've got projects that are really thinking deeply about how to make this accessible to all, both really rich data sets that allow good thinking, but also the tools to help describe that, I think it's a really huge step in the right direction. So I'm going to let Danny tell you more about those steps.
Thank you. I think the first rule of speaking is to know your audience, and I don't know this audience, so just help me for a second. I gather that some of you are teachers and some of you are students. Is that right? Who are the students? Well, we're all students, I guess, in some sense. Okay. And your students at GW or here or here? All right. GW, back there. Now, yeah, the college students sit in the back. They don't like that. Okay. And then those of you who are teachers, how many of you teach statistics, or how many of you don't teach statistics? Okay. And so what do you teach?
No, I'm just a statistician at the Fish and Wildlife Service, but I mentor kids, so.
Oh, great. So I'll be interested to see what you have to say, to hear what you have to say. And there was someone else who doesn't? A biology professor. So you use stats or you came to the wrong address?
I use stats.
Okay. So I'm going to tell you something that will probably seem completely obvious to everyone who does not teach statistics and won't make any sense to people who do teach statistics. And what I want to say is that statistics is about data. It's about making sense of data, about extracting information from data. It's not about proving things. That can be a tool in very rare occasions for statistics. It's about approaching the data and honestly taking away the information it contains. And doing that honestly requires judgment. So those who do teach statistics probably know that it's hard to teach statistics, and largely that's because you're trying to teach judgment. And Carol's anecdote about the .048 is an illustration of that, because every textbook you pick up is going to say, is it less than 0.05, which sounds like a mathematical statement. But actually, just in the last few months, and 2 years ago, the American Statistical Association, which is down in Alexandria, right? Yes, across the river, they said, stop with the p-values already. Right. Don't use the term statistical significance. It never had any meaning, and it has even less now. And yet, if you look at textbooks, you will see statistical significance and p-values and tests of various sorts all over the place. So there's this odd disconnect between what practitioners, I don't know about the Fish and Wildlife Service, but what practitioners in statistics are doing and the techniques that they're doing, and the material, largely historical material, being learned by statistics students. So that's what I want to talk to you about. And as another way of, get this window up. That's not up. That's no good. All right. For those of you who are teaching or taking an introductory statistics course, or an advanced one for that, I want to know what is it that's in your course? And I've listed a few things here just because people are shy to start listing things out. But do people study the two means, difference between two means? And two proportions? And the slope of a regression line? And ANOVA? Okay, not yet. It's interesting that people don't get to ANOVA because it takes them to, I don't want to put words in your mouth, it takes too long to get through all the other stuff before you can get to it.
And the ANOVA is the good stuff.
The ANOVA is the good stuff. Why is it the good stuff?
So it lets you look at multiple things, which is real. It helps you make more sense of the real data that's sort of messy.
So could you give a short, I'm putting you on the spot, a short definition of ANOVA, or what you think of? If I said ANOVA is about t-tests but with more categories, does that sound great to you? Because that's what textbooks say it
Right.
is.
See, what I'm doing is all the stuff, that article that just came out said we shouldn't be doing. That's what we're doing in my department. We have like 8 sections of intro stats. None of us have stats background. We're all math professors, but we need to teach statistics. And so I'm coming to figure out what I should be doing.
Okay.
Because I keep reading what I shouldn't be doing.
And when you study inference, I mean all of these things about inference, two means, two proportions and such, do you use formulas and tables? Like do you have to calculate the degrees of freedom in a t-test, which turns out to be some fraction, and then look in between the lines to pull out a critical value? That kind of thing, not anymore? Okay. How many people use computers? Bootstrapping, resampling, randomization-based techniques? Okay, so you learned statistics after 1970, then, if you're using those things.
Old dogs can learn new tricks.
Yes, old dogs can learn new tricks. Okay. I just want to find out a bit more. And for graphics, what kind of graphics do you do? Do you do histograms and box and whiskers? People do stem and leaf plots?
Yeah.
Yes, that's so interesting. Stem and leaf plots, and then you do scatter plots and box and whisker plots. Is that right?
Yeah.
And anything I'm leaving out? You'll think about it later. I'm not like the congressman who's going to say, why didn't you say anything about this when you were getting
Right.
testimony? But those are the kind of graphics you were doing. And I'll say something about stem plots. Stem plots were invented by a very eminent statistician named John Tukey. And they were his attempt to make it possible for people to do graphics on a typewriter. And do you all use typewriters when you make this stem?
No.
That was the whole point of stem plots, was because people didn't, sketching it out by hand looks bad. And so you could make it look fancy if you typed it out. And this was a way of typing out a handful of data. You can judge for yourself whether that's a major concern these days in how we do graphics. You study experimental design? What do you learn about experiments? It's early.
We just started actually. We're doing like randomness and like kind of basic probability.
Basic probability, okay? Anyone want to say something else about what they do in experimental design? Yeah.
I guess it's not so much the mathematics, but just how you choose your factors and the sample sizes for each and what you're trying to generalize to, and that you want, you know, if you have a cause before and after or some, you know.
Right. Right. It's a rich subject.
Yeah.
I assisted in an AP course at Cardozo High School a few
Yes.
years ago, and was using one of the AP books, and it had a lovely chapter on just a sort of a qualitative chapter about experimental design that talked about the concepts. And since I had never done experimental design as a mathematician,
Right.
I was doing, the other kind of statistics. I found it very interesting.
Okay. Sampling bias, is that something you talk about? And you do that mostly anecdotally, I think?
Yeah.
there's not really a mathematical framework for it. There is, but there's not one that you talk about. How about causation? What do you learn about causation?
Correlation is not causation.
No, what do you learn about causation? You told me that something is not causation. Tell me what causation is. What do you learn about that?
You can only get it from experimental.
You can only get it from experiments.
You can't get it from observation studies.
And so what happens if you can't do an observational study? Like you want to find out about this vaping and whether it really is the vitamin E, is that what it is, or something like that, in the substance? You're going to do an experiment. There's some people vaping with vitamin E and some people without.
There's ethical issues.
There's ethical issues. So if we can't, so we couldn't say anything about causation. So I don't know why you want to ban the vaping if you can't say anything about causation. Is causation an important thing to you all in Fish and Wildlife?
Well, I mean, you want to infer causes, but yeah, so we...
Because you're interested in like promulgating policies and rules and things like that.
Right.
And you want them to have an effect that's desired. So you need to know what will be caused by your interventions in the system.
Right. So we build models that describe and different, so that we can decide between different policy alternatives. So I guess the causes of that, yeah, I don't know if, I haven't gone through the causal statistics stuff, so that's
Okay,
where
but then you know that there's causal statistics.
Yes.
Yes. So I'm going to tell you something about correlation and causation. Correlation is causation. I didn't drop a word there. Right? I know that's not what the t-shirts say, and it's not what the textbooks say, but it is in fact the case. If A and B, some variables, are correlated, then there's 4 possibilities. Either, I mean substantially correlated. I don't mean just sort of, oh, maybe by accident it's cheesecake eating and the stock market or whatever.
significantly correlated.
Well,
No,
yeah,
I'm
but
kidding.
If you look at enough stuff, you'll get significantly correlated things. I mean things that, you know, where seems to be a substantial correlation. Either A causes B, it's one of the 4 things. Either B causes A, another of the 4 things. Either C, some other thing, causes both A and B, a common cause. There's an organization here, I guess, called Common Cause. That's the 3rd one. And then the 4th one is a little bit obscure. It's called a collider. And most people, even in statistics, haven't heard about it. And it's where A and B both cause C, but aren't connected to each other otherwise. Those are the 4 possibilities. There are elaborations on them, and sometimes you have to uncover which one of those 4 it is. Those are the 4 possibilities. There's no other possibility. So when you find a correlation, it's up to you to decide whether you think vaping causes lung illness or lung illness causes vaping. And most people have an idea about that. And long ago, Fisher said that there's a common cause for smoking and cancer. And it was only in 1960 that he was shown mathematically to be wrong. Right? Experimentally, no one could do the experiment. It was all observational data. But mathematically, he was wrong. There is, in fact, a mathematics of causation. And it's something that's essential if you're going to take data and infer from it, however imperfectly that may be, infer from it what the result of an intervention will be. But I think your summation of what's in the textbook about causation is very untargeted. Confounding and covariates, you do. You said your state?
I've heard of the term.
Yeah.
Okay, but it's not featured. It's not like a major thing.
Statistics.
Okay. Anything I'm missing here that's sort of the summary of the stats courses? What?
Probability.
Probability is very interesting. There's a report called GAZE, among other things, that says You don't really need it. If you want to teach that, that's fine, but it doesn't really have anything to do with statistics. That surprises a lot of people since many so-called statistics courses are actually entitled probability and statistics, which is kind of like saying camels and statistics. Yeah, you might need to ride a camel to get something.
Sample surveys.
Sample surveys, right? And you know, sort of biases in them, or sample
Construction as well.
construction,
As well as.
things like stratified samples or
Cluster or
clustered data collection.
Data selection.
Okay. Other things I'm missing? I didn't put on this list. I'm not really missing them.
well, I don't know, sort of principles of inference, or how you take the data and collect it to represent, you know, to make generalizations, or
So sort of external validity kinds of issues? Is that what you're thinking of?
not. So you can get a bunch of data, you can learn correlations and all this stuff about it, but if you want to relate it to outside the data set,
Right.
you know, you have to think about how the data were collected, and
And so are you thinking about the sort of thing? A statistic versus a parameter, a sample versus a population, that
Yeah.
kind of inference? Okay. Populations are an interesting thing because no one ever sees them. But it's another matter. Other things that I'm missing.
Would hypothesis testing go under experimental design?
Under inference, I put it, yeah. What I'm missing is data. Right? And you said, I think, sir, that you spend some time talking about collecting data. Right?
Talk about types of data.
Types of data, levels of measurement, many different quantitative kinds of things. How about data wrangling? How about what a database is? It's not just a bucket of data.
right.
Right? What are relational operators? Data cleaning?
I mean, that's what we spend like 98% of our time on.
Data cleaning. Yeah, so that's the joke, is that 90% of data science is cleaning data, and the other 10% is complaining about cleaning data.
Right.
And you know, collecting data, well, that's great. And especially in Fisher's day, where statistics was being used exclusively by people doing benchtop experiments or agricultural field experiments, designing experiments was absolutely synonymous with statistics. But then people discovered that statistics is much more useful than that. And then there are other people who've been collecting data who aren't thinking about what it would be used for. For example, Google, or Twitter, or Amazon, right? Those are just the commercial sources of these things. There's remote sensing data, there's all sorts of genetics data out there, completely different in size and complexity than the kinds of data, difference between two means, that you study in statistics. And to me, it's very interesting that, in fact, data is not central to statistics. Things you do with numbers are central to introductory statistics, but not data. Not how to pull it in, acknowledging that someone else is collecting it. Not how to clean it, reshape it for the purpose that you have. That's not part of statistics. So in stat prep, we saw this as a problem. And we were, the MAA, the Math Association of America, along with the ASA and AMATIC, this two-year program, they were interested in what's going on with data science. And they wanted to make it possible for people who do not have training in statistics, which is what most statistics instructors are, in fact, that they could learn something about data. And then there was another motivation, that when mathematicians teach statistics, if you give them any way out, they will teach probability. You nod your head, and so when I believe we can make it impossible to turn a statistics course that's actually about data into one about probability. So I want to show you some ideas that we've had and some materials we've put together to make it easier for people to teach with data. And I don't mean the kind of data that you get on problem 6.14 in the statistics book, where it says 6 rats were swimming upstream with this velocity. Can you show that it was different from 0? I don't mean that kind of data. I mean data of the sort that address contemporary issues of interest. Data of the sort that someone would make a decision based on. The decision might be something trivial, like, should I recommend this book to the person so that they'll buy it? Or should I recommend this movie so that they'll click on it? Right? Those are all decisions being made, but there are also important decisions being made. And so, what we wanted to do is help faculty out, most of whom are trained in mathematics and not in statistics, help them get started. And ideally, we want to make every graphic, and I say every, but every graphic based on data. It's an interesting exercise to turn the pages of your statistics book and see what fraction of the graphics actually have data in them. It's almost 0. Right? There's lots of graphics about normal curves. There's lots of graphics about the theory of statistics, but it's not rooted in data. Not rooted in data. And also, because we're living in a more complicated world and it's not simple benchtop experiments, we wanted to help people move towards a more integrated perspective, ability to model, not just talk about the difference between 2 means. Why would you Why would you care about 2 means? In biology, sometimes you have 3 of this and 3 of that, and you want to use the mean. That's a really small data problem, and there it's appropriate. And multivariable. Statistics books always start out with a single variable. I don't know what you're supposed to do with a single variable. Right? What statistics is about is explaining the variation in something. Right? You're wearing a red shirt, you're wearing a pink shirt, I'm wearing a gray shirt. Right? That's variation. Explain the variation using some other factors. It's because old people are gray and young people are vibrant and pink and red. That probably is not a very good theory. But there's always got to be some explanatory variables. And then we want to focus on contemporary practices. So contemporary practices, data often have hundreds of millions of rows. I'm not even going to go there. Let's talk about 50 cases. Right? That altogether, if you stick to data with more than 50 cases, half of an introductory statistics course becomes irrelevant because they're techniques designed for very small data sets. There was a reason they were designed that way, but that's not now. And also, we want people to be able to make responsible causal claims. It is not enough to say A and B are correlated, therefore A causes B. That's not a responsible claim. But bringing in additional information and doing additional work with potentially other variables, that does allow you to make a responsible claim. Is it a guaranteed true claim? It's statistics. What do you want? What do you mean by true when you're talking about the real world? It's complicated. And also, this is a strange omission, statistics isn't about prediction. Or at least statistics teaching isn't about prediction. Because that wasn't the point. The point was to figure out whether this fertilizer increased the growth of plants. So you do an experiment. It wasn't what's going to happen next year if it doesn't rain in November. But those are the kinds of problems that people are very much interested in now. Being able to give a range on predictions, I would think, would be very... I know about fisheries, but I don't know whether that's what you call...
Birds.
What?
Birds.
Birds, okay. So, that's ideally what we wanted to do. But we also wanted it to have an effect. And so, what we're doing is helping instructors teach their present topics, but do it in a way, do it with data. Right? Not that those are the topics that should be taught, but that's what people are comfortable teaching, and they can make a transition to using data. We want to make it easier for instructors to use real data with real questions behind it, which always involves knowing something about the system that you're studying. And that's not a tradition of mathematics. Mathematics has a tradition of abstraction, and it's a proud tradition, I'm not criticizing it, of posing toy problems, right? Because they can be stated precisely. But that's not what statistics is for, to provide a stadium for posing small problems. And then computing. Those of you who are taking statistics, what kind of computing do you use? A TIA, graphing calculator? Is it a graphing calculator? Yeah, graphing calculator. You use graphing calculators at Bishop Moreland? No? Well, maybe you want to take a summer intern and have them show you how to do it. You got to get on the ball here. What is it that you use? Paper and pencil?
You're right. Yeah. No, I've been using S plus and R since like the 1980s.
You use computers. These are not rare instruments anymore.
Danny, when I went to the Department of Energy after retired from academia, I actually used my TIA.
At the Department of Energy?
Yeah, after I left Minnesota, I went to work for the Department of Energy.
I also worked for the DOE in the early 80s. So, but
But I did use my TIA degree to show people. So I found it.
and again, to put the biologist on the spot here, those TI-83s, they're all over your biolab? No. What do you use instead?
Well, I use R for my students. So.
Okay. So R, for those of you who don't know, is a kind of leading statistics package. And there's been a whole history in the development of statistics software over 60, 70 years now. And it didn't involve the TIA before. It involved things like SPSS and SAS and Stata. And R is one of the modern versions for this, very widely used. And it's what we use in the stat prep project. So we'll talk about 3 levels of computing. Right? It's just not meaningful. Statistics is a computational discipline. And the algebra was introduced because people didn't have computers, and they needed to make approximations in order to solve these puzzles. But now we can just do the calculation over and over. It's very tedious. It's not humanly possible, but we have these machines for doing it. And so I'm going to mention 3 levels of computing. The one I'm going to talk about most, and I'll get to it soon, we call little apps. And these are student-facing, meaning that even for instructors who aren't familiar with computing, they may want to use them also. But students don't need to have any background in coding. No background at all in coding to do this. And you'll see some examples. So that's kind of the sort of thing that just about any student can start off. If they can do Facebook, they can do this. I can't do Facebook. And then the second level are what are called tutorials. And these are highly scaffolded exercises that involve actual code. But the code is structured in a way so that all you have to do is change some potentially little thing. So they're really exercises in reading code rather than in writing. And as programmers will tell you, if they're honest, it's more important to be able to read code than to write code. Because if you can read code, you can find something that does almost what you want and tweak it to do something more like what you want. That's how almost all software is written, is by making little tweaks in things. So being able to read code, to see what things are referring to is very important. And then there's the kind of programming which is kind of blank page, and you start to write down some stuff. Right? That's genuinely writing. That can be very hard. right? And it helps to have training. And that's what most people think about when they think of statistical computing, is this sort of de novo writing of code. But these days, all of them can be done with browser-based software. It's not true that every student has access to a browser. We work with, in Stat Prep, one of the members of the leadership committee works with schools in Arizona on reservations. And they have just dismal conditions. But in DC, it's often a library. Some students have, do you have laptops? Yeah, okay. So there, they have a laptop. Have you heard this internet thing? No, okay, I didn't think so. You don't look that smart. Have you? Have you ever connected to it? Yeah.
Occasionally.
Occasionally, like in the last hour. All right, so you don't need to install software, you don't need to buy software, you just need the little apps we're trying to make work on a phone. Now, not everyone has a smartphone, right? But the little apps work on a phone. All right, so I'm going to mostly talk about number one, and then, but I just want to say something about these tutorials. So these tutorials are web documents, and they have little panels in them. I'll show you a picture in a second. They have little panels in them where you can type. And we give them a set of computer commands that has a highly consistent syntax, so that people are not learning obscure things about syntax. So just to say, this is a variable. It's being explained by that variable. There might be others in there. Where's the data coming from? And in this case, I have to say what I'm looking for. Right? But for this one, I want to make a scatter plot. There it is. A box plot, same command. Right? I just have to ask for a box plot instead of a scatter plot. I want to do a linear model, which encompasses everything you do in intro stats that's even remotely correct. Calculate a median. Also, see, the syntax is very, very consistent. So you can focus on what you want done and what the relationship between variables are, and not have to worry about brackets and curly braces and semicolons and things like that. And there's a link which I think is available on the website, but I'll just show you. Here's a tutorial. And we wrote these for instructors so that they would feel more comfortable working with computers. And so this is a document on the web. It has some narrative in it. This little box here is a complete session in which you can do any statistical computing that anyone ever needed to do. But we're only asking people here, well, what am I asking people to do here? You tell me. See if you can have learned to read the code.
Calculate the mean height of the data set.
Calculate the mean height from the Galton data. Okay, how about this one? You use R, don't?
Is it a cross tab for the mean height by sex category?
Yeah, so it's the mean height for the sexes, whatever you want. That's what these tutorials are. And people can learn to use it the same way Duolingo works. You know, you have to change a word, right? There might be more blanks as you get more advanced.
So my question is, and this is what we keep running into, we want to use, like, Pearson has, StatCrunch, there's all this stuff built in to a lot of things, but the academic integrity piece for if you still are going to give any kind of traditional exam or something, how do you deal with that when you have to go on to, unless you do a lockdown browser kind of thing, how do you deal with that? That's part of, I'm just being honest, that's part of what makes us resistant, because we already have academic integrity issues to begin with.
Yes, absolutely.
In stats, and so then how do you go to something that's more out there and open and real data without, how do you do it?
Well, so let me tell you what I do at Macalester, which is a relatively rich institution and has students who are, it's a very selective institution. They all have computers, right? And they don't want to use computers in the lab, right? They all have telephones in addition to their computers. How do I deal with that problem? My tests are on paper. you can ask completely appropriate computational questions on paper, right? I could give you this and say, okay, change it so that it does height broken down by 6. Even if I wanted to ask a purely computing syntax question, I can do that. And it's just not worth the hassle to me and the risk, as you understand, of doing things on the computer. They do their homeworks on the computer. If they don't do their homeworks on the computer, you're not going to pass a test on paper which asks them about even simple things. So the fact that you use a computer for some things does not mean you have to use it for everything. And testing is one of those areas. There are technical solutions, but they're cumbersome. And for me, I just said, I'll do it on paper. So this is that intermediate level. I guess I talked about a blank page. Here's the advanced level of computing where you start with that. But I'm going to talk about little labs. So I'm intentionally not going to show you one until after I've told you what they are. All right, so it's going to seem tedious. So I don't know why it says, do I just need something here? Obviously, I didn't put in the picture I meant. All right, structure of a little lab. So point number 1, the central display is data. It's not a probability distribution. It's not a QQ plot. It's not any of those. It's not a stem and leaf plot, which is one variable. And there's 2 axes on a graph. You learned that? What do you call them?
X and Y.
And what are X and Y? Variables. Okay, there, we've got it. So the graphic has 2 axes. Each of them is a variable. Now you're pulling from the algebra tradition where a variable is an unknown. And these are variables in data where they're known. But so each axis is a variable. So not density on this axis and something else on that axis. Whatever it's going to be. Sex and height, income and education, whatever it might be. And every unit of observation is shown. It's not a schematic. Each case, each row in the data is a dot. Now, when you get to 100 million, no, it doesn't work that way. But if you're doing 5,000, no problem having all those little dots on the screen. So that's the first thing. It's data-centric in a very literal sense. Data, for reasons of simplicity, we provide data sets along with these little, but it's possible to add any data set into it that we want. And 2 that we use, just to give you as an example, one is from the National Health and Nutrition Evaluation Survey, which is something done in an ongoing way. And the data that we have students work with has 10,000 rows, so not a big data set. And 76 variables. Right? Not 1 variable, not 2, 76. And why 76? Well, because it's nice to be able to come up with an idea about what might be interesting, and then use statistics to see if the data support that. As opposed to, here's 1 variable, here's another, turn the crank, get out the p-value, it's 0.048, now you have to think, because it's 0.048. Another one, the CDC, Centers for Disease Control, publishes data every year on every registered birth in the US. And I think the vast majority of births are registered. There's about 4 million births each year. And we have those available, but it's too large to use on this web system. Use it on your laptop, no problem. But on this web system, so it's only 100,000 births. And there's 45 variables. And some of them have to do with socioeconomic status, who the baby, how much the baby weighs, what was the baby's ACVAR score in 5 minutes, things like this. So again, giving you the ability to explore, not just calculate a result. Yes, sir?
It's a random sample.
This one is a random sample, and genuinely a random sample. Yeah, but it's always the same one when you're using these apps. So you'll see in a little bit.
It is always.
Say again?
You say it is always or not always?
It's the same random. We have those 100,000 in the data, so it's not going again and picking it up. But there is something like operation. The student picks typically 2 variables. a response variable, and an explanatory variable. And this is the language that gets used actually in statistics. There's other terms that are equivalent, but this is the language that gets used, not this group and that group. They're variables, two variables. And you can optionally pick a covariate, and sometimes you can pick more than one, depending on what the method is that we're demonstrating. All right? And the student picks a sample size. Why that? Because so much of our class is about sample size and how the sample size affects what you can see. Now, to be honest, what we tell them the sample size says you can say is not right. There's always other things going on. Right? It's a theoretical construct, the best possible, the narrowest possible interpretation you can put on this. So when you get into the world of big data, then you have to stop using this language of significance, or even looking at, the confidence intervals are very tight. That's fantastic. But why were you looking for the mean? What was it that you really wanted to know? So, but students pick a sample size, and then they can collect a new sample at the push of a button. So the sample is from that 100,000 or 10,000. So they might set I'll show you. That's the operation. And then statistics are always annotations on top of data. Right? There's also tabulation, regression table. That's not shown in the graph. That's shown underneath the graph, and you can refer to it. But the graphic and the data are central to all of these things. And we have a very simple, limited vocabulary for graphics that actually lets you express yourself much more richly than the huge variety of words for snow that exist in statistical textbooks. Instead of leaf plot, dot plot, bar plot, all of these different things. So we've really tried to narrow it down. And inference, well, the first thing about inference is to see what it's about. That if you got a new sample, the result wouldn't necessarily be the same as the original sample you had. And that you can kind of see how much variation there is. And that it depends on the sample size. Some of the apps involve bootstrapping directly, just to explain that concept of bootstrapping. And students can vary the sample size. So you can make a sample size of 10 and see all of this crazy variation, make a sample size of 1,000, and now it's looking really smooth. And then I mentioned statistical tabulation. So this is for instructors, a suggested pedagogy. First, introduce data. So what does it mean? Data come in tables, there's rows and columns, variables, units of observation, there's categorical variables, there's quantitative variables. If you want to talk about the types of quantitative variables, okay, but first talk about data. And then let them at it to plot out data and look for patterns. And you don't have to tell them what patterns are in data. When there's something there, they're going to see it. Oh, it's not just a big cloud. It looks like that. So they will see patterns. Then talk about patterns, have them explore patterns, give them ways to describe patterns. If I fit a function to it, it would be a straight line or a curve or whatever it is. Or we look at the difference in means between these two or three levels of the explanatory variable. So you've got formal ways to describe patterns, that language, slopes to one. And let them have it. And they will find all sorts of relationships in the data. A lot of them don't exist. That's really important, is that they discover that you can't just look at a small set of data and say, oh, there's definitely something going on here. Right? Or this thing that I saw, well, it turns around when I get a new sample. Right? They discovered that the hard way. And then it becomes a problem of interest, how to avoid those false and then we can introduce formal measures of sampling variation. Right? So confidence interval will be a formal measure of standard variation. Why we use standard errors, I just can't figure that out. And we're always going to multiply them by 2, but that's the history of statistics. And then we can talk about the formal methods for figuring out sampling variation when you only have one sample. When you can make as many samples as you want, it's easy to see sample variation. But when you only have one sample, then there's some tricks. Tricks aren't necessarily hard, but then there's some tricks. And that's the statistics course. Now there's experiment, there's bias. We're not dealing with that here. Just sort of the inferential data presentation. What you might call it technical. So let me show you a little lab. And I have this one queued up. I don't have internet. So this is available on a browser. And if you have a browser with you, you can go to that address now. This one is not yet set up for cell phones. It takes up too much space. So you can see that here's the graphic. How many variables are there in this one?
3.
What are they?
Sex, age, systolic, whatever, pressure, minus blood pressure.
And the fourth one, the education level.
Yes.
Now, is this a meaningful variable? No, I don't know. That might be the question. Okay. So there's graphics here, and each case is a dollar. So the sample size I picked was 1,000. The response variable is systolic blood pressure. Explanatory variable, really a covariate is an explanatory variable too, but we just call it something different to get this role clear. Pick an explanatory variable, optionally pick a covariate. In this one, you can facet those five little pens. And then there are some controls which differ from app to app, depending on what the app is intended to teach. So you could fall, let me bring it up. Watch it crash. That's the most fun thing. That's not it. Yeah, okay. So this is point clouds. This is the one I just showed you. For some reason my cursor goes away. Shown in a web browser. Okay, so this is just about graphics. It's not about analysis of the graphics, but you can learn a lot from graphics. So I'm using this National Health and Nutrition Survey. You could use something else, but let's just keep it straightforward. And this has things like systolic blood pressure, urine output, height, weight, income, age that you smoked marijuana for the first time, those kinds of things that you hear. So we have a choice of, we have a choice of response variables. Why do we have a choice? Because you should be able to pick something that's of interest to you. So, you know, whoever wants to call out something, say again?
Like home rooms.
Home rooms. Okay. So I'm going to make that the explanatory variable, and let's pick out
Income.
income. Great. Let's look at income, and then the response variable will be the number of rooms in the home.
Oh, is that what you?
Yeah. Not which old room you've been assigned to. I'll make
This is on the
2,000 points. Actually, I'll make it 1,000. And then I'll stratify. Oh, I don't stratify. Okay. And so it's hard to see what's going on here because the income is actually in categories. I'm going to do something called jittering. And you'll see immediately what it does when the graphic comes up. Because this is actually quantitative. Well, there's a bug. That's nice. All right. Let me change from what.
This is the N. Haynes data?
What?
This is the N. Haynes data?
Yeah.
Wow.
I'm going to pick
You can pick something other than home.
your pulse. And something, this
Oh,
one
okay.
is a I'll make it genuinely categorical. Diabetes, okay, also diabetes.
Depressed.
So you see anything obvious there about the difference between the pulse rate of people without diabetes and people with diabetes? No, there's nothing there. And actually, that's what hypothesis testing was invented by Fisher for. It wasn't exactly Fisher, but was to say, nah, there's nothing there, go on. It wasn't to say, oh, there's something there. It was to say, no, there's nothing there. Move on, get more data, do something. Let me show you another one that has more action to it than this one. Because this is just about graph. And there's my trying to get here. Okay. Usually these are on the web, but since I don't have a web connection, let's do a t-test. T-test is something that shows up in just about every intro stats course, I think. Okay, and here I've got age, and now in the t-test I can only use variables with 2 levels. That doesn't seem like a limitation when it comes from a textbook. But when you used to be able to plot things with 5 levels, it seems, well, why am I working with this case? Nothing I can do about that unless I move over to. So whether or not you smoke and your age, and let me stratify the sample, which is say put equal numbers in the 2 groups, and make it a little bit bigger. Okay, so age is vertical axis. Whether you smoke is on the horizontal axis. What do you see?
Older, you have more people that don't smoke.
Yeah, that among people who smoke, they tend to skew younger. All right, and do I need to do a test, a Kolmogorov-Smirnov test or something like that to get at it? I don't. Right now, it's a hypothesis. Why would smokers tend to skew younger?
They die off earlier.
There's a theory. Is it the right theory? I don't know. Right? But being able to investigate covariates, for example, looking at their general health, for example, is a covariate. I can't do that in a t-test because the t-test doesn't offer any room to include other variables. So it doesn't matter how precise the t statistic is you calculate. You're not asking a question that might need to be asked. So here, I'm going to turn on the mean.
Did you censor the data?
The NHANES did.
Yeah,
So something goes wrong. That's not. I'll change from age to body mass index. There. Okay, something's. All right. Did I open up the wrong one? Did I open up the development version? What did I do here? Is there an internet that I can sign on to?
You have a hotspot on your phone, sign on to yourself.
You guys probably know better than I do. What? I can't hear you.
So it's DCPS Math.
Yeah, I'll just.
Oh, there's the guest. Do you see the guest? Oh, it looks like it's open.
What's the code
Okay,
for
great.
it?
I don't, can you, this, oh, guest doesn't work. Okay, try mesh then.
You can use his phone as a hotspot.
I'll just use my phone. I mesh on.
Yeah, clearly.
And all I need is a password.
Okay, I got it.
All I have to do is click that little button.
Of all things. Well, I guess it's happy.
Thanks.
It's like you get a 1 for putting your name on. Look at your leg. I know. Who the fuck?
So I'm going to start out just so you can find these things yourself. This is statprep.org. This is the site that we all work with. And It's just a ordinary web page. Under resources, there's something called sources, little apps, and then there's a bunch of these things. There's the point plot, enter in. I said I would do t-test. It's not letting me get there. All right, I'm going to take another one, and then I'm going to move on. But sorry about that. How embarrassing. That's not the way things are supposed to work. Let's look at proportions. Let's look on proportions. Oh yeah, so this is about the difference in proportions. And so the response variable has two levels, right? Because we want to know which proportion is alive or dead, or Democratic or Republican. I guess there should really be a big neither in there. But, so the response has two levels. And here it's female and male. I'm going to make it a little bit different. Let me make it whether you own your home. Okay, so either you own it or you rent or something else. And I'll make the explanatory variable. Come on. They work better than this one. I'm making the explanatory variable age. All right? So do you own your home as a function of what your age is? What do you see?
Old fogies are more likely to own their home than younger folks.
Do you want me to bring fogey up as a covariate? To test that theory. Okay. So, you know something though? This isn't the test that you do in intro stats. Right? We're doing regression with a binary outcome as opposed to the difference in two proportions. It's not particularly hard to think about regression with a continuous variable here. There's no reason why that should be excluded from our course. Just that the formulas are too hard. Okay, but the computer does the formulas. So you can see what the proportion is at age 0. I'm not sure, that must mean they live in a house that their family owns, or else there's a bunch of rich kids out there. And by the time you're 80, many, many people own. So these little apps, when they work, give you some options to explore. So here, instead of this, I'll use logistic regression. You notice the change for those of you who worry about logistic regression instead of linear regression? It's pretty minimal. I can get a new sample. Does that line change? No? Okay. Well, let me do it with just 100 points. There's the line. Even 100 points seems to be plenty of data for doing it. Let's do it. 10. No, I don't think I've got a reliable indication here of what the rate is. And I can see that directly just by pressing new sample. Now, I need to give you something to contrast this with. And again, I apologize for it not working. It's supposed to work. I just opened up the wrong project or something like that. But, all right. So there's all sorts of apps here. I'm going to show you some contrasting apps. There's a lot of apps out there. Some of them come with textbooks. They have their own apps. Like the Lock 5 people have their own apps. And you said you used Pearson. What was the book that you used? The publisher? In back?
Yeah, it's definitely Pearson.
They have their own apps.
They have StatCrunch.
StatCrunch, okay. And this is a set of apps that was written by a guy named Dan Adrian, who's a professor, and I'm blanking on what school it is. And I'll show you what it means not to be data-centric. And I'm not criticizing him. In fact, we featured these apps on
5 minutes.
5 minutes. We featured these apps on the StatCrunch site. But that's an app, and you may well have seen apps that are kind of like that. Where's the data? Right? I mean, you get to experiment. This is about that formula and making sense of the formula. It's not about data, you're choosing the mean, you're choosing standard deviation. So that's an example of, and many, many apps that you find in statistics are about that. And it's appropriate, because the formulas are murderously hard for many students. The fact that you don't need them, well, that's another way of solving the problem. All right. Oh, here's the t-test. The t-test app that I wasn't working when I brought it up on my own. And you see the statistical annotations there. You could probably figure out what the blue I-beam is, confidence interval on the mean. What the red I-beam is. So this is, do you smoke or not? How old are you? Well, that's what we were looking at. The confidence intervals don't overlap. Done. You don't need anything else but that. But for reasons that are a little bit hard to explain, we start to over-quantify it because we're looking at p-values like 0.001, right? And then the confidence intervals really don't overlap. But all you need is to look at the confidence intervals and see they don't overlap. Another one, this is a multiple regression app because you can easily do it. You don't have to fit straight lines when the data obviously are not on a straight line. What does that say to students when you're drawing a line that doesn't go through the data very well? So we want to give you a little bit literally of flexibility here. And then there's more to say about what those bars are on the right side. All right. So the point I want to make is that data can be at the center of a statistics course. And it's not a light statistics course or a frivolous statistics course. It's a statistics course that can get at the big issues that are covered in introductory statistics and also issues that they never get to because they're so wrapped up in the technology of 1910 in doing these calculations. And so being able to interactively experiment with data, form your own hypotheses about it, will you be able to check whether that hypothesis is right? No, you might need new data. But if something appropriate is there as a covariate, that can help you do it. So about exploring, about seeing sampling variability by sampling many times, and then showing that the statistical artifacts, the confidence interval, they're a good summary of sampling variability. But there's really nothing you need to know beyond that for a confidence interval. And it's about sampling variability, not about what else. All right, so I talked too much. I'm very happy that
15 minutes, because so you just said we have to be done here by 5:30.
5:30.
So we can rush out, you know, so the point is 15 minutes for questions.
Yeah.
Okay, Ashley? Okay, Ashley,
Actually, I'm going to give you a minute to figure out what you want to ask while I get a drink of water.
oh, sorry, that's my fault. I forgot to bring water.
You scared him away.
I wasn't sure if you were asking
You should
first
just give
or
him his
something.
mug early.
It's my fault. I usually remember water. Oh, yes, yeah. 15 minutes also.
While our speaker is getting a drink, I have a comment on one of the questions you asked earlier about the academic integrity. I have not been actively teaching in the classroom since the 90s, but back then with my intro business staff students, I would give each of them different data.
Yes, we've thought about that. We have like 8 sections. So we've tried group exams, we've tried different permutations of things, but the classes are large, we have 35 students in the class. So, and we're all, I'm just going to be honest, like any one of our classes could take up all of our time, and then we have research and university service and everything on top of it. So it's also being efficient. Like, you know, there's that point of diminishing returns. So obviously we need to make it more real. But how to do that in an efficient way, that we actually do it and we're not. I'm very aware of introducing, I'm a little hypersensitive about introducing misconceptions. Like when you don't know something deeply, it's so easy to introduce a misconception. And so I tend to try to err on the side of not misspeaking. Because you have to generalize. Well, it makes sense for the students, right? And how do you generalize without overgeneralizing? a big question for me.
Okay, so you had a question.
Yeah, so my
Can you
question.
use this microphone, please?
Yeah, especially for the
Oh, gosh, okay. Thank you. So my question centers.
The microphones are just recording.
So my question centers around secondary data. So most students won't really, in their political science or sociology courses that they take in college, aren't going to be expected to apply methods to the data. They'll be expected to pull in secondary data from the CDC and kind of draw conclusions from that. And so I wonder, where does that leave secondary learning and understanding secondary data in intro to statistics?
Well, let me just ask while you've got the microphone. So by secondary data, you mean the kind of tabulations that these sites will put up?
Right, data that
Like the
is
Census
already,
Bureau?
Right.
Oh, summaries already.
Right.
Good, good. Okay, so the secondary data, maybe we call pre-tabulated data. Does that sound like what you're getting at?
Yes.
The secondary data is an artifact of an age when it wasn't possible to send large amounts of data around or to tabulate them readily with what you have at home. There are still many organizations that distribute only tabulated data. The CDC, though, is pretty good at giving you what might be called the raw data. And whether you want to have students clean or give them already the clean data, but there are lots and lots of sources out there that are raw data. And if you have them see what the data is behind the tabulation, there are certain misconceptions that you can avoid, like the ecological paradox, things like that. So yes, this approach is not set up for already tabulated, reduced data. And insofar as you want to teach about how to handle specific data sets in that format, this wouldn't be appropriate. But I would argue that in introductory statistics, the broader statistical, or what is a tabulation, for example, is probably a more central issue to what you want students to learn.
Who else has a question?
I noticed that you were talking about bootstrapping as one of the tools. How have you used bootstrapping in an elementary, what I would call an elementary statistics course? I just wondered how it's interpreted.
How bootstrapping is interpreted?
Yeah, I mean, you're taking a sample, and then you're making a lot of subsamples by duplicating the things that are in it, and you can show some variation in intervals and things. But what does that say about the population from which it is drawn, or is that not the question anymore?
So bootstrapping is used to get confidence intervals. And one of the great misconceptions students have is that confidence intervals are about the population. Right?
I guess that's my misconception.
So there's this fiction that the population, whatever that might be, has a mean, has a parameter called the mean. Right? And that's how this is interpreted in the standard way. But it's utterly adequate and more honest to say the confidence intervals tell us how precise our estimate is. We don't know where the true thing is. But this is an honest statement of the precision that we're entitled to given the data that we've got. So when you get into things that involve models, the model is the modeler's thing. Right? It's subjective. It addresses a question that the modeler is interested in, and if causation is involved, it incorporates the causal assumptions that the modeler has. And so it seems kind of odd to say that the population has a parameter for the modeler's model. But somehow the mean is so simple that people forgot that that's just one thing you can ask about data. Happens to be one that's algebraically tractable, but it is just one thing. And it may not be what you want. I think I have this slide here. I'll just see if I can find it very quickly. I'm going to show you a terrible example. I'm going to show you an example of math scores on the SAT for boys and girls, for, high school students, all right? And I'm sure that many of you here understand that women can't really do math, right? You guys math professors, you understand that. Where could such an attitude come from? It's crazy, right? Well, here's a t-test on the SAT math score versus sex. And look at that. What does that tell you?
Very, very small.
The p-value is very, very small. Or to use the terribly misleading language, it's highly significant. Right? That's because I have, I think, 10,000, about 10,000 students data here. Maybe I'll do it graphically. What does that tell you?
Not really different.
It says that the women who do really well are outliers. That's a funny thing to say. All right? And look, all the lines are lower for the women than they are, except the very bottom. Right? There's equality between the sexes at the very bottom. But let me show you the individual data points and what kind of message you get from those. So each dot is a person, and the blue thing is called a violin plot. It's like a density plot, but it doesn't consume an axis. I think when you look at that, you have to say, yeah, men and women are the same. Now, are they really the same? Well, looking at the mean doesn't get it back. So you can ask a very precise question about the mean and get an answer. But it's not the answer that's important. The answer is that most guys are 500, and most women are 500. And that for guys and women, there's fewer as you get up towards 800. I think that's a more honest display. Right? And it's because you're showing that we're interested in describing variability among people, right? As opposed to variation in a mean, in a statistic. It's the people who are.
All right, do we have any other questions?
Oh. So, right. So how do you worry how much the data is generated? Like, oh, I've got data here and it's men and women, but it's those people that took the SAT and maybe it's in a part of the country or
Absolutely.
whatever. So
I'll just ask you, since you deal with across the country, wildlife birds across the country, I'll just ask you, what states do you think have the highest SAT scores? The average SAT score, for high school seniors taking the SAT.
Minnesota.
Yes. Well, North and South Dakota are often higher, right?
Oh, okay.
Mississippi beats Massachusetts every time.
Oh.
And it's not because you're wrong about schools in Mississippi.
Fewer students take the SAT.
That's right. And in the Midwest, students take the ACT. It's only if you're going out of state that you're going to take the SAT. And so, who's going out of state? Typically better students are going out. Not always, but typically better.
Like Minnesota, where he taught and I taught, the parents, I taught at a state school and was in a private school. But I would have parents come to me, well, my boy can go to Madison or the Twin Cities because he's male and that's safe for him. But my daughter, that's not safe, so she's going to come to Winona State.
Okay, let me give you a regression problem based on real data. So again, looking at SATs. I'm not saying SATs mean anything,
Right.
but we do have them. If you look state by state in SATs and you plot out expenditures per pupil in public schools and SAT score, right? So I'll put it on this axis. What do you think the regression line would look like? This is expenses.
Yeah, so higher expenses, higher SATs.
Okay? And when you do the regression, you find out that it goes the other way and that there's no ambiguity in it. It's completely statistically significant. Right?
Okay.
It's not that there's an influential point, all the standard tests and regression. So how could that be? The reason is that same thing with the number of students taking the SAT. If you adjust for, control for the fraction taking the SAT, you see that in fact, SAT doesn't change very much with expenditures, but it does show a significant positive.
So if you're going to take it and you don't have a whole lot of money, you might be the better students to make it worthwhile. Or
Right, I mean, whatever Mississippi spends, there are excellent students in Mississippi. Right? Why shouldn't they get 800s? But most students don't take the SAT in that state. When Maine implemented the SAT as a requirement, statewide testing, the scores went down.
Right.
All right, so we're gonna have to wrap this up. So, thank you so much for coming. We have a gift for you as well.